Welcome back to Mathematics Lifeline. In today's video, we're going to do 10 integrals, but they keep getting harder. So we're going to start out really easy with level 1, and by level 10, we're going to have a pretty tough integral that we need to solve. So let me know how you do in the comments. I'd be glad to hear how you do, but we're going to go ahead and get started with level 1. So level 1 is the integral of 3 dx. Now, I'm sure a lot of you are looking at this and you're thinking, really, this is level 1? Like, this is too easy. But again, we need to start easy so that we can ramp it up a little bit. But anytime we integrate a constant, so 3 is just a constant, right? The integral sign and the dx are just kind of part of the notation, but the 3 is what we're actually integrating or taking the antiderivative of. So anytime we do that, we just multiply it by an x. So we get 3x, and then we need to add an arbitrary constant c. And again, with all of these integrals, you can check that they're correct because the derivative of this, well, the derivative of 3x is just 3, and the derivative of a constant is 0. So when we take the derivative, we get back to what we started with at 3. So yeah, that's it for level 1. We're going to go ahead and move on to level 2. Okay, so for level 2, we're going to integrate x squared plus 4x minus 6. Now this one, again, is not too hard, but I want to remind you of the property we're going to use here. We're going to use the power rule. So the power rule says the integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. So we're able to do that for all of these terms here. So if we take x squared, right, in this case, n is equal to 2. So when we use this property, we know that this one is going to turn into x to the 2 plus 1. 2 plus 1 is 3. And then we divide by that same number, and that same number is 3. So we have x cubed over 3 for this part, plus this one. This power is actually a 1. It's not written, but it's implied that this is an x to the first power, so we're going to use the same thing. So we're going to have 4x to the 1 plus 1, which is 2, over 2. And then, again, with the constant 6 right here, all we need to do is multiply that by an x. So we have minus 6x, and then we add the constant c. Now, we're not going to call it there because this term right here can be simplified. So we're going to have x cubed over 3. That one isn't going to be able to simplify. Plus, this one we can simplify the constants, right? We have 4 divided by 2, which is a 2x squared. And then we have minus 6x plus c. And that right there will be our answer for level 2. So again, it's not too bad, but we're going to go ahead and start ramping it up a little bit right now. So here is level 3. All right, so here we have level 3. This is the integral of the quantity 3x plus 2 raised to the 50th power. Now, this looks crazy. And if we were going to do this using the power rule, we would need to distribute this 50 times into itself, which that would take hours, right? We're not gonna do that in this video. But what we can do is the process called a U substitution. So we're gonna take this entire term in here, and we're gonna make that equal to U. So we're gonna say U is 3x plus 2, and of course we need a du for this method, which is the derivative of u. Now, the du here is going to be the derivative of 3x, which is just 3, and the derivative of 2 is 0. So du is just 3, but we took that with respect to x, so it's going to be 3 dx. Okay, so the whole point of a u substitution, and I'm sure you're familiar with this, but the whole point of the u substitution is to replace all of our x variables with u's. So we want to eventually replace this dx. So we want to solve for dx here, that way we can replace it. So we need to divide every side, or both sides, by 3. So we'll get du over 3 is equal to dx. So now we're able to immediately switch this, right? We're going to change dx to du over 3, and we're going to change 3x plus 2 into u. So we rewrite the integral. We have the integral, well, this just turns to u to the 50th power, and then the dx turns into du over 3. Okay, so if that's du over 3, what we're going to do is, since these are being multiplied, we can just move that constant into the front. So we'll really have 1/3 u to the 50th du. And from there, I think it makes it a little bit easier to move the 1/3 out of the integral. So finally, we'll have 1/3 times the integral of u to the 50th du. And you can see now that this is just a power rule. This is directly in the terms of a power rule, so we're able to evaluate it that way. So the 1/3 kind of goes along for the ride. So we have 1/3 times. The integral of u to the 50th is going to be, using the power rule, u to the 51st over 51, right? And then outside of that, we'll have the plus c. Now, we can go ahead and distribute this in. So it'll end up being u to the 51st over 3 times 51 is going to be 153 plus c. But this is not our final answer because remember, we need it in terms of x, and we have u here. So u was 3x plus 2. So our final answer is going to be 3x plus 2 to the 51st over 153 plus c. And that right there will be our final answer. So the method we used there was u substitution. This is typically the first thing that you learn after you study just the basic power rules and basic rules for integrals. So yeah, that's it for level 3. We'll go ahead and move on to level 4. All right, so here is level 4. So here we have the integral of the inverse tangent of x squared over 1 plus x squared dx. Now, I will admit this question looks really, really tough, but if you understand u substitutions, you'll see that this is actually it's not hard. It looks harder than what it is. It's very simple. So we're going to do another u substitution. Now, the way we're going to pick our u here is going to be, we want to think about the derivatives of what we have. So if we chose u to be anything down here, right, the derivative of this denominator is just going to be 2x. And that doesn't help us. That doesn't help us get rid of anything. However, when we have tangent inverse, remember, if we choose that to be u, so we'll say u is tangent inverse of x, the derivative of that is 1 over 1 plus x squared dx. And we have a 1 over 1 plus x squared, right? If this was gone and we just multiplied fractions, that's exactly what we would have. So notice that if we rewrite this integral as the integral of, we'll say, tangent inverse of x squared times 1 over 1 plus x squared dx, this is the same thing because this would just go into the numerator when you multiply the fractions. But you see that this entire term right here is actually going to turn into du, right? So then we can just replace this tangent inverse that we have in here, that'll be our u. So then what we have when we change this into the u world is going to be u squared du. All of this will go away and turn into du because they're equal. So we're just integrating u squared. Integrating u squared is not hard, so we're going to just say that that is u cubed over 3 plus c. And again, this is not our final answer because u cubed over 3 is in terms of u. We need it in terms of x. But remember, u was tangent inverse of x. So our final answer is going to be inverse tangent of x cubed over 3 plus c. And that is it for level 4. Now, I realize that this is a shorter question than level 3, but I think a lot of people will look at this and just be scared of it, right? Inverse tangents aren't fun to work with. Inverse trig isn't fun to work with, especially in calculus. So you'll look at this and you think it's harder, but really it's not. This is just a standard practice of u substitution. But yeah, that's it for level 4. We're going to go ahead and move on to level 5. All right, so here we have level 5. This is the integral of x times sine of x dx. Now, here you have to notice what we have in this integral. We actually have a product here. I didn't write the multiplication, and typically you won't, but we do have a product of two functions here. And typically when we have a product of two functions, what we're going to want to do is we are going to want to use integration by parts. So remember the formula for integration by parts. It's uv minus the integral of v du. So with integration by parts, we need to choose a u and we need to choose a dv. So that's the important step. Now, if you don't remember how to do this, remember with u, we want to choose something that when we take the derivative of it, it's going to get easier to work with. So notice if we take the derivative of sine x, it just goes to cosine, and that derivative is negative sine, and that derivative is negative cosine. It just kind of goes in that cycle. But if we take the derivative of x, this will actually reduce down to 1. So we want to choose u to be equal to x, which means that du is equal to 1 dx, which is just dx. So that's good. We want that. Now, that means that sine x dx, right, this whole part right here needs to be our dv. So we have sine x dx. And remember, to get back to v, we need to integrate sine x. Well, we know the integral of sine. The integral of sine is going to be a negative cosine of x. It would be a plus c, but I'm not going to add that because we'll add in a plus c at the end. So now that we have all of these, we want to transform that into this formula. So we have uv. So uv is this times this. So what that's going to be is a minus x cosine of x. And then we're going to subtract off the integral of v times du. Well, v is minus cosine of x. So we have minus cosine x. And that's times du, and du is just dx. So now you can see we have this term, and we're subtracting off an integral that we know how to work with, right? This is not a product anymore. This is just one function. So we're able to integrate this in the standard way. Now, what I will do is I'm going to move this negative out so we don't have to work with more negatives than we need. So we're going to have a minus x cosine x out here. This will end up being a plus the integral of cosine x dx. And now the integral of cosine x is very, very elementary, right? We know how to do this. So this is going to be a minus x cosine x plus the integral of cosine is sine x. And then now we've integrated everything we need to, so we're just going to have a plus c at the end. And this is our answer. So the important thing about level 5 is realizing that we have a product of functions in here, which means we need to use integration by parts. So we were able to get that done, and we get our final answer of minus x cosine x plus sine x plus c. So that's it for level 5. Let's go ahead and move on to level 6. All right, so here we have level 6. This is the integral of 1 over 16 minus x squared raised to the 3 halves dx. Now, this integral is pretty tricky, and some might even debate that this should be higher than level 6 because people struggle with this method. But what this is a trig substitution. So we have the form, and you might need to review your trig subs here, but what we have down here is we have something that's in the form of a squared minus x squared, right? And if this is the case, that means that a is equal to 4, right? Because 4 squared is 16 minus the x squared. So that's what we have. Okay, so in this case, when we have a squared minus x squared, we need to use a substitution. It's based on triangles. So what we're going to do is we're going to set up a triangle to figure out what we need to use. So we have, here is a right triangle. And we'll say that this side over here is x. We'll call this angle a theta. And then this a right here is actually going to be our hypotenuse, which is 4. So the hypotenuse is going to be a, and the reason is because if you think about the Pythagorean theorem, let's say we wanted to solve for this side length, right? We're going to have the hypotenuse squared minus this side length squared, right? That's 16 minus x squared equals this side. So that's where we're getting this substitution from. But what we want to do is evaluate for x. So if we know that sine theta is equal to opposite over hypotenuse, which is x over 4, and that implies that x is equal to 4 sine theta. So we're actually going to use that substitution for x. Now what we need is a dx, and that's just the derivative of this. So we have dx is going to be equal to the derivative of 4 sine theta, which is going to be 4 cosine theta. But remember, we took the derivative with respect to theta, so we need a d theta on that end. Now, because of this, we're going to actually work with this right here. So here's what we know. We are going to say we have 16 minus x squared to the 3 halves. So we're going to work with that first. So we have 16 minus x squared to the 3 halves. Well, if we use this substitution, we're going to have 16 minus x was equal to 4 sine theta. So 4 sine theta. And that is squared. And all of that is to the 3 halves. Now we want to do a little bit of simplifying here. So we're actually going to square this. So we're going to get 16 minus 16 sine squared theta to the 3 halves. And then we still need to work with this a little bit because there's not really a good way to integrate this yet. So what we're going to do is factor a 16 out. So this is equal to, so we're going to have 16 times, this will be a 1 minus sine squared theta. And all of that is to the 3 halves. And now we're getting somewhere because remember, 1 minus sine squared is cosine squared. So this is really equal to 16 cosine squared theta, all to the 3 halves. Okay, so this is what we have for this bottom part right here. Now, what we want to do is we want to try to even simplify this a little bit more. And the reason is because we can actually work with this to the 3/2 power. So what we have is if we take 16 and raise it to the 3/2 power, you can do this on your calculator, you do it however you want. This is going to give us a 64. Okay. Now, if we take cosine squared and raise it to the 3/2, remember we multiply these exponents. So 2 times 3/2 is just going to be 3. So we're going to have cosine cubed theta. Okay, so this is a lot of simplifying, right? But what this does is this ends up replacing this part. So we're going to rewrite the integral. This 64 cosine cubed is going to replace the denominator. So 64 cosine cubed theta. And then we're going to want to replace our dx because now we're trying to get this in terms of theta. So if we replace dx, remember that was just 4 cosine theta. So we're going to have 4 cosine theta, and then we'll have the d theta out here. Now what we can do is we can simplify this because 4 over 64 will reduce to 1 over 16, and that's just a constant. So we have 1 over 16 is coming out here times the integral. Then we'll just have cosine theta over cosine cubed theta, which is going to be 1 over cosine squared theta. And again, we have d theta. Okay. So from here, we can actually simplify this 1 over cosine squared theta to secant squared theta. So this is 1 over 16 times the integral secant squared theta d theta. And remember that the integral of secant squared theta, we're able to change that into just tangent of theta, right? Because the derivative of tangent is secant squared. So ultimately, we're going to have 1 over 16 tangent theta plus c. But remember, we started out in the x world. So how can we get theta in terms of x? That's where this gets a little bit trickier. So the reason this gets trickier is because we need to go back to this triangle that we set up. Remember, we want to look for something that's going to change tangent theta because that's what's not in terms of x. This is a variable, and we need to change that back into x. But if we know that using this triangle, we were looking for this, right? And this was 16 minus x squared. So what that means is that tangent theta is opposite over adjacent. So opposite over adjacent is x over this square root. So what that means is that we really have 1 over 16 multiplied by tangent of this theta. And that's going to be x over, so we'll have x over square root 16 minus x squared. And then again, we have the plus c. And that right there will be our final answer. So this is a really tricky question. Level 6 is tough. If you're good at trig subs, this is pretty standard practice here. But a lot of people struggle with this. This is a very hard concept when you first see it. But this is our answer. And if you need any help on this one, feel free to ask me in the comments because this was a tricky question looking back. But yeah, that's it for level 6. We'll move on to level 7. All right, so here we have level 7. Now this question looks so much easier than anything we've done so far. So we have the integral from 0 to 1 of 1 over x dx. Now the reason this is level 7, and it's really not that hard of a question, but the reason it's level 7 is because typically when you're learning strategies for integration, this is the last thing you learn. So this is what's known as an improper integral. And the reason is because, remember, if we're doing the definite integral of 1 over x, it's easy, right? That's the natural log of x. You probably have that memorized. The problem is our bounds that we have here. Notice that in our bounds, we have from 0 to 1. But if x is 0, we have 1 over 0, and that's undefined. So we want to think, how can we deal with this problem? And the way we're going to do this is we're going to set up a limit. So we're going to have the limit as x approaches 0. Actually, we won't do x. We'll do another letter so that we don't interfere with this one. So we'll do the limit as b approaches 0 of the integral. We're going to change that 0 into a b, and this is going to be a 1. And then again, we're still integrating 1 over x dx. Now, this is okay, and the reason is because if we integrate this now, it's okay because this is a limit. So it never actually equals 0. We're looking at the limit as b goes to 0. So what we're going to do is we are going to integrate this as normal. So we're going to have the limit as b goes to 0 of the natural log of x evaluated from b to 1. So then, using that fundamental theorem, we're going to be able to solve for this. So we're going to have the limit as b goes to 0 of, we're going to have the natural log of 1, right? So the natural log of the absolute value of 1, and then we're going to subtract off the natural log of the absolute value of b. So when we do this, we're going to have the limit as b goes to 0. The natural log of 1 is always going to be 0, so we're going to have 0 minus the natural log of b as b goes to 0. Now remember that as b goes to 0, we're only looking at it from the positive direction as it's coming in from the right side, because from the left side, well, natural log functions aren't defined for negative numbers. So as b goes to 0 from the right side, remember the natural log graph looks like this. So as b goes to 0 from this side, we're seeing that it's going to actually approach negative infinity. So this will end up being the natural log of the absolute value of b. I guess I shouldn't have wrote the limit, right? This is what we have. Now we're going to say that this is 0 minus, as b goes to 0, this becomes negative infinity. So 0 minus negative infinity, of course, gives us positive infinity. So what do we write down for our answer? Well, we're actually going to write down that this limit diverges. And that will be how we deal with this improper integral. And the reason it's improper is, like I said, we have to look at the domain of this function, and we know that this is not defined for 0. So this limit, or this integral, diverges, and we got that by doing an improper integral. So yeah, that was level 7. Again, I don't think it's as hard as the last one that we did, but these improper integrals tend to trick people up because people forget that this is not defined at 0 and they just do it normally, and you'll get it wrong like that. So we have to make sure that we're working on, identifying the domain of our original function. But yeah, that's it for level 7. We'll move on to level 8. All right, so here we have level 8. This looks like a very simple integral, but it actually is really tricky. So we have the integral of secant x dx. Now, at this point, our integration techniques that we would want to try aren't going to work because we can't do any u substitution, we can't do any trig subs, we can't do partial fractions, which we'll see actually in level 9. We can't do a lot with this one. So we need to manipulate the function itself. So here's how we're going to do that. We're going to say this is the same thing as the integral. We still have secant x, but we're going to multiply by something in the numerator and denominator. That way we can actually work with this in a familiar way. So we're actually going to multiply it by this function. So we're going to have secant x plus tangent x. We're going to multiply by that in the numerator and denominator. And the reason is because this means when these divide, they just become 1. So it doesn't change what we have in here at all. So now we're going to rewrite this function as we're going to multiply the secant x into the numerator. So we're going to have secant squared x plus secant x tangent x over, the denominator stays the same. So we just have secant x plus tangent x. Now, you may not see it immediately, but we can actually use a u substitution here. If we set u equal to secant x plus tangent x, that means that du is the derivative of this. Well, the derivative of secant x is secant x tangent x plus the derivative of tangent x, which is actually secant squared of x. And you can see that dx out here as well. You can see that du actually encompasses this entire part up here. So this entire thing will become our du. And you can see how nice that is because it takes everything away. Right? We have the secant squared x, we have the secant tangent x, they're being added, and we're multiplying by dx. So we're going to rewrite this integral in terms of u. So you can see how much easier this is now, because now this is just the integral of 1 over u du. And this is pretty easy, right? Remember that this is going to be the natural log of the absolute value of u plus c. And remember, this is not our final answer because u was secant x plus tangent x. This is going to be equal to the natural log of the absolute value of secant x plus tangent x plus c. and that will be our final answer. Now, most of the time when you have the integral of secant x, you'll have this in a table. You won't have to do this in your classes. But if you don't know how to do this integral, this could definitely be really challenging because this is such an abstract thing to think to multiply by. But you want to force a u substitution, and that's how we can do it. But yeah, that's it for level 8. We'll move on to level 9. All right, so here we have level 9. This is the integral of 3x squared plus 7x minus 2 over x cubed minus x squared minus 2x dx. Now, this integral, we can't do any u substitution. We can't do integration by parts. So the way we're going to approach this is we're going to use partial fractions. And that's why I have this as level 9, because partial fractions are something that you may or may not have learned, and people struggle with it a lot when they come into calculus. So this is going to be partial fraction decomposition. So what we're going to do is we're going to work with this entire fraction real quick. So we want to rewrite this so that we can integrate it pretty easily. So we want to rewrite it to where we're going to have a over some factor plus b over some factor plus c over some factor is equal to the whole thing. So 3x squared plus 7x minus 2 over x cubed minus x squared minus 2x. So we need to factor the denominator. So the way this is going to factor, we can factor an x out of this. So we'll have x times x squared minus x minus 2. And this will actually factor into x plus 1 times x minus 2. And if you multiply this out, it'll give you what we have right here, x cubed minus x squared minus 2x. So what we're going to do is we're going to take these factors, and they're going to go in our denominators of these fractions. So we'll have a over x plus b over x plus 1 plus c over x minus 2. So this is our partial fraction. Now what we want to do is we want to figure out what a, b, and c are so that when we add these fractions, we end up with this entire fraction. And that way, we'll be able to rewrite this in a form that we can integrate. So the first step with partial fraction is we're going to multiply everything here by this denominator, right? We want to get rid of this. So when we do that, remember this was factored into this. So we're going to multiply everything by these three factors. So we're going to multiply everything here by x times x plus 1 times x minus 2. Now when we do that, we're going to come down here. So when we multiply this one, the x's will cancel. And we'll end up with a times x plus 1 times x minus 2. And then we'll have plus b times, now remember, x plus 1 will cancel this time. So we're going to have bx times x plus 1 canceled, so that all we'll have left is x minus 2. And the same thing with c. The x minus 2 will cancel, so we'll have plus cx times x plus 1. And this is going to be equal to just the numerator, right? Because this will cancel out everything down here. So it's equal to 3x squared plus 7x minus 2. Okay, so now what we're going to want to do is we're going to want to expand these out. So we're going to FOIL this, and we're going to multiply everything by a. So when we do that, we're going to get an a x squared. So that's the x times the a. And then we'll have minus 2x plus x. That's minus x, but it's also times a. There's going to be a minus ax. And then the constant, we have 1 times negative 2. That's going to be minus 2a. Then we'll have plus b x squared, right? Because we're multiplying here and multiplying by the b. And this one will be a minus 2bx. We're going to do the same thing with the c. So we're going to have a plus cx squared plus cx. And that's, again, equal to 3x squared plus 7x minus 2. Okay, so this is where we can solve for a, b, and c, because we're going to equate all of these x squared terms with this one. So if those are going to be equal, that means that these coefficients in front of x squared need to add up to give us 3. So that tells us that we have ax squared, so we need a, we'll have plus b plus c should end up giving us 3, right? Because we have these are x squared terms, so when we add these constants, it should give us 3, so that we'll get 3x squared. So that gets rid of this, this, and this. Now we want to look at the x term. So we want all of these terms that just are being multiplied by 1x to equal 7. So that's going to be a minus a from this one. We'll have a minus 2b from this one, and we'll have a plus c should be equal to 7. So that gets rid of all of our x terms here. And now we want to equate what's left with this constant term. So we want minus 2a to equal minus 2. That's the only thing that's left. So negative 2a should equal negative 2. So now what we have here is a system of equations, and we can actually solve for these variables. So what we're going to do is we're going to say, okay, if we know that negative 2a equals negative 2, that means that a should be equal to 1, because negative 2 times 1 gives us negative 2. So now if a is equal to 1, we're going to go ahead and sub into these two equations. So we'll have 1 plus b plus c is 3. So we need to subtract this 1 over. So we'll get b plus c is equal to 2. And in this one, if a is 1, we'll get a negative 1, which we can add over. So we'll get a minus 2b plus c is equal to 8. So what we're going to do is we want to solve this system. And this is much easier because we can just subtract these, right? If we subtract, we'll get rid of the c's and we can solve for b. So b minus negative 2b is going to give us 3b. These cancel when we subtract. 2 minus 8 is negative 6, so equals negative 6, which means that b is equal to negative 2, right? And now if b is equal to negative 2, then we have negative 2 plus c is equal to 2 from this equation, which implies that c is equal to 4. Okay, so we've done all of this work, and we figured out that a was 1, b is negative 2, and c is 4. So what we're going to do is if we know that this plus this plus this gives us our original function, we're going to rewrite this integral in terms of these partial fractions with a, b, and c. So this is the same as the integral of 1 over x, because that was a was 1. It's going to be a minus 2 over x plus 1. And then we'll have plus 4 over x minus 2 dx. Okay. This is something that we can integrate because these are all going to be natural log functions. So because of that, for these ones, we would kind of need to do a u substitution technically, but because the derivative of what we would choose to be u is 1, we don't really need to do it because it wouldn't change the outcome at all. So we're just going to integrate this directly. So the integral of 1 over x is the natural log of the absolute value of x minus 2 times the natural log of the absolute value of x plus 1, right? That's how we would do this. We would do a u sub. We would set u equal to this, and then the du would just be 1, so it doesn't affect what we have. So that's why we're able to skip straight to this part. And the same thing for this one. Du would end up being 1, so we can just skip that step and put plus 4 times the natural log of x minus 2. And don't forget the plus c, and that right there will be our answer. So this one is tough because if you don't remember your partial fractions, you're going to have a lot of issues here because that's really the only way we can break this down into a form that we know how to integrate. So partial fractions is very important for a lot of these integrals. But yeah, that's it for level 9. We're going to go ahead and move on to the final level, which is level 10. All right, so here we have our final level, which is level 10. Now this is the integral of e to the x times sine x dx. Now, just like one of the previous levels, this is a product of functions. So your first thought should always be to go to integration by parts. And that's what we're going to do. So we're going to use integration by parts. So we're going to say we need a u and we need our dv. So it doesn't really matter which one we choose here, and here's why. This is why this question is a little tricky. If we're working with these functions, think about the derivatives and integrals of it. The sine, right, these trig functions, they cycle between sine, cosine, or negative sine, and negative cosine. And e to the x is going to stay the same every time. So it really doesn't matter which one we choose. But we're going to work with u equaling sine x. Like I said, you can do it either way. I'm going to pick u equals sine x, which means du is the derivative, so that's cosine x dx. Now dv is going to be the one we left over, so it's going to be e to the x dx, which means that v is equal to e to the x. Okay, now remember our integration by parts formula is uv minus the integral of v du. We're going to need to use that a couple times for this question. So we're going to rewrite this integral as uv, right, which is e to the x times sine x. So we have e to the x sine x minus the integral of v du. Well, v is e to the x, du is cosine x dx. Okay. Now, let's look at what we have here. We still have another product in this integral. Now, what that means, and typically that's okay, but we're just going to need to use integration by parts again. So we're going to have to do it again. So we're going to do the same thing. U is going to be cosine x this time, because it's still that trig function, which means du is minus sine x. That means that dv is going to be the e to the x dx. There should be a dx here. And then v is the integral of that, which is just going to be e to the x, because it stays the same. So again, we're going to need to do the same thing, but with this integral. So we're going to have e to the x sine x minus. Now, this integral in here all turns into another integration by parts. So we need to put this bracket so that we can distinguish it. So we're going to have a minus uv, which is e to the x cosine x, minus the integral of v du, which is going to be e to the x times negative sine x dx. Is going to be a minus e to the x sine x dx. Okay. Now what I'm going to do is I'm going to rewrite this again. So I'm going to say this is equal to e to the x sine x. I'm going to get rid of this bracket here. So we're going to have a minus e to the x cosine x. Now what I'm going to do is I'm going to get this constant out of here. So this will actually turn into a plus inside the bracket. But when we distribute the minus, it's going to go back to a minus. So this is minus the positive version of e to the x sine x dx. Okay. So look at what we have again. This right here is another product. So we would need to use integration by parts again. But the trick for this one is that we don't. And here's why. If you notice, this is what we were trying to integrate. This function right here, this integral, is the original question. So what we're gonna do is we're gonna call this I. Okay, that's the integral, which means that this right here is also equal. Actually, not the whole thing. That's what it looks like. This is equal to I. So what we end up having is that I is equal to e to the x sine x minus e to the x cosine x minus I. And now you may be able to see what we're going to do here. If we want to solve the integral, we want to solve for I. So we're going to move all the i's to one side. So we're going to add I over here. So that means that we're going to have 2i is going to be equal to e to the x sine x minus e to the x cosine x. And then to solve for I, we're just going to divide both sides by 2. So that tells us that I is equal to e to the x sine x minus e to the x cosine x, and all of that is over 2. And that will be how we find our antiderivative there. So yeah, this is level 10. I think, honestly, there were a few that could have probably taken this one's place. This one is tough just because if you don't notice that this is your original integral, you're going to be working in cycles forever. And you're probably going to think you're doing something wrong, when in reality, this is exactly how you're supposed to do it, but you have to end up solving for I in the end. So yeah, this is it's a tough integral only because you need to notice this trick. But yeah, that's it for the 10 integrals that get progressively harder. I hope you enjoyed this video. I hope you got them all right. If you did, that's great. I know level 8 was a little bit tricky because you kind of had to think about what to do and how to force a U substitution there. So it is a tricky question. Hopefully you were able to get that. But yeah, if you like this video, if you like these types of videos, let me know because I really enjoy making them. Of course, if you have any questions, feel free to let me know. My comments are always open. But if not, then I will see you in the next video. Thanks for watching.